All right, let's go ahead and talk about them. So just as a reminder, to be separable, you have to be able to write it as y prime or dy dx, whatever you want to say, equal to a function of x times a function of y. That's the requirement to be separable. We don't always end up writing it exactly like that, but you have to be able to get it to look like that. So then you can bring the y's to the left and the x to the right. To be a first order linear differential equation, you have to be able to write it as y prime plus a function of x times y to the first equal to some other function of x. Also, for those of you watching the video, you should definitely stop, work on these questions, determine if they are separable, first order linear, neither or both, and then watch the rest. So this first one, even though it might not look like it's separable, it's totally separable. We are writing the right-hand side as a function of x, 25x, times a function of y, which is 1. When I'm thinking separable, or the potential to be separable, yeah, whenever it's separable, I really want to write it as dy dx, or d whatever, because it makes it easier to see how to bring the y's to one side and the x's to the other side. So if I rewrite 1 as dy dx equal to 25x, it becomes really, really clear that I can rewrite this as dy equal to 25x times dx. And that definitely shows me, oh, it's separable. But the second one here, second one's a little tricky. Second one definitely is written in the format that looks like it's first order linear. And it is. You definitely have your derivative plus a function of x times y to the first equal to 0. It's also separable. So this one is actually both, because you can certainly write it as y prime plus your function of, I guess it's a function of t, plus p of t times y equal to q of t. It's just that in this case, our p of t happens to be 8, not very exciting, and our q of t happens to be 0, also not very exciting. But this certainly does qualify as being first order linear differential equation. But we could also make it separable. We could totally write this as dy dt equal to negative 8y, and then we can bring the y's to the left and the t's to the right. So we can write it as 1 over y dy equal to negative 8 dt. I will point out that when you're separating, if you have like constants on one side or the other side that you want to multiply or divide, it's pretty standard practice to leave them on the right side, the independent variable side, like the dt or the dx or whatever your independent variable is. So that's usually what people do, but by no means do you have to do it that way. You could totally have divided the 8 over as well if you wanted to, or the negative 8 even. It just usually seems like it's easier to leave it on the other side. Question so far? Okay. Let's do this third one here. So this third one, so when I'm asking myself if it could be first order linear or separable, well, specifically, if I'm asking if it could be separable, I would bring the y, I would leave the y prime on its own, and then if I have everything else on the other side, it seems like it's really going to be hard to factor out the y's from the x's. So this third one's probably not separable. I can see that if I have x to the fourth times y prime equal to x squared minus x, why am I saying if I could just write it down? If I do this, equal to x squared minus x cubed y, it's going to be really, really hard to separate the x's from the y's. If these were both x cubed, I could totally factor out an x cubed. I have x cubed times 1 minus y. It would totally work. But I can't here. So it's probably, it's not separable. Is it first order linear? Well, the thing I would always ask first if I'm thinking about first order linear is, do I have y prime and do I have y to the first? If I have those two things, it's potentially possible. If I don't have those two things, it's definitely not possible. I do have them here. I have a y prime, I have a y to the first. I need to rewrite it in this format just to make sure that I can actually see that it's first order linear. But that's not too hard to do. If I divide by x to the fourth, I'm going to see, okay, x to the fourth y prime divided by x to the fourth plus x cubed y divided by x to the fourth equals x squared divided by x to the fourth. And that's going to become y prime plus 1 over x times y equal to 1 over x squared. And that definitely is a first order linear differential equation. I've got my y prime, I've got my p of x, I've got times y equal to my q of x. Let's look at the other ones over here. Let's see how many. Sure, I can do it this way, I guess. So looking at 4 is definitely separable as well. We can, I guess I could write I could say this one's first order linear differential equation. So I should write the answers. Can you see that? Yeah, you can. Okay, for number 4, when you've got things multiplied like this, I think it's pretty straightforward to see. Oh yeah, it's separable. We can totally bring the y's to the left and the t's to the right. So I have 1 over y times dy equal to 60 t to the 9th dt. You don't even have to do that work, but I like showing how they separate if I'm going to say it's separable. Okay, let's look at 5. 5 doesn't look like it's anything specific, but it's totally separable, right? We've already got all the x's on the right except for the dx. We just have to rewrite this as dy dx equal to e to the 6x plus 9x squared plus cosine x. I mean, this is really more of a 16b type of problem, right? Solving this differential equation really just means you're anti-differentiating the right-hand side, right? You would get dy equal to e to the 6x plus 9x squared plus cosine x dx. And then if you actually wanted to solve this one, because it's not hard to do, you can anti-differentiate both sides. Let's write it this way. The antiderivative of 1 times dy equals the antiderivative of e to the 6x plus 9x squared plus cosine x dx. So sometimes a differential equation looks very straightforward. It's just solving an antiderivative like we would have way back in 16b. And yeah, I guess we could solve this. You're going to get y equal to e to the 6x over 6 plus 9x cubed over 3, which is just 3x cubed plus sine of x plus c. I know I said not to solve them, but this one seemed like I couldn't help myself. I'll take 6. Maybe we can fit these all in here. dy dx equal to 13y. Well, that also is separable. We're going to bring the y's to the left and get 1 over y dy equal to 13 dx. Very standard differential equation. Let's see, 7 over here. 7 over here was kind of an afterthought, I will admit. 7 is definitely neither. It's definitely not first order linear. Specifically because it's not linear, right? We have a y squared. If it was a y there, it would totally be first order linear. But since there's a y squared, it can't be first order linear. And it's definitely not separable. If we try to get the y prime by itself, let's check it out. I have x squared times y prime equal to 5 minus xy squared. There's no way to break apart that right-hand side as a function of y times a function of y. I suppose we could even go to y prime equal to 5 divided by x squared minus xy squared over x squared is going to be xy squared over x squared. Right? There's no way to break the y's and x's apart. So this one is definitely neither. And lastly, number 8 over here, some change of variables here. dr dt equal to 6t e to the r. Now, usually I do look for separable first because it's easier. This is definitely separable, but I want to point out it also couldn't be first order linear. Again, it's certainly first order because we have a first derivative, dr dt, but it's definitely not linear because the function, the thing that's the function. So actually, I should ask you both. What is the thing that is the function here? Is it r or is it t? It's not. T is the independent variable. R is the function of t. So right when we write like dy dx, we're thinking that y is a function of x, and where this dy dx represents how y changes as x changes. So whenever you're writing d whatever, the thing on top is your function kind of thing, and the variable on the bottom is your independent variable, your input. So here, r is the function thing, and t is the independent variable. So if we were going to solve this, not that we're going to solve it, but the solution would be some sort of r of t equal to whatever. what I wanted to point out is it's definitely not first order linear in the function r, because although you have dr dt first order, it's not linear because you have e to the r. E to the r isn't a linear function of r. So, excuse me, this one definitely is separable. We can write it as dr over e to the r equals 6t dt. Or I would actually probably write it as e to the negative r times dr equal to 6t times dt. Okay. Questions about any of these before we keep doing some more stuff? We're going to solve some of these, but I wanted to show you. It's really good before you start just applying a method to make sure that it's the method you should be applying. And these are the only two methods we've really got. I should ask you both, what are you talking about in class just now? First order linear. So yeah, that's typical. Did you no, you might not have. I don't imagine you've talked about Newton's law of cooling yet. Okay, cool. Yeah, it's not that funny. All right, come on. Get over yourself. All right. So let's take a look at some other examples. And we're going to come back to a couple of these, but there's a couple problems to have in mind, specifically solving some oh my gosh, what's the word I'm looking for? Some particular solutions. This is kind of like that, but not exactly. So suppose we have this solution, y of t equal to 8e to the negative 5t, and it's a solution of y prime plus ky equal to 0. We also know that y of 0 is y naught. Okay. I do want to point out, just to kind of emphasize the thing we were saying before, y is your function thing, and t is your independent variable. And they're not asking us to solve this. They've already solved it for us. All they're asking us to do is figure out what k is. So we know that y prime plus k times y should equal 0. So if we want to figure out what k is, what we need to do is substitute in what y and what y prime are and figure out what k has to be. So we already know what y is. Y is 8e to the negative 5t. So if I know that y of t is 8e to the negative 5t, how am I going to find y prime? We have a function. How do we usually find its derivative? We take the derivative, right? I mean, like, it's like, duh, of course. Yeah, we do the thing. But so let's see, if I want to take the derivative of 8e to the negative 5t, it's going to be 8 times e to the stuff times the derivative of that stuff, which is negative 5. So putting these things in, right? So y of t is going to go in for y, and y prime of t is going to go in for y prime. We're going to get, I'm going to make this, so it's going to be negative 40 e to the negative 5t plus k times 8 e to the negative 5t is going to equal 0. So what does it look like k needs to be? Yeah, 5. I mean, you could do the work, right? It feels kind of silly, but you could say like k times 8 e to the negative 5t equals positive 40 e to the negative 5t, and then divide both sides by 8 e to the negative 5t to get 40 e to the negative 5t divided by 8 e to the negative 5t. And these parts cancel out, and 40 divided by 8 is just 5. So k equals 5. You don't have to do all that work though to see it, I don't think. And then y naught is actually probably the easier part to solve. So y naught is just y of 0. Well, we know what y of t is. Y of t is 8e to the negative 5t. So y naught, which is y of 0, is just 8 times e to the negative 5 times 0, which is just 8. If you like, you can write it as 8 times e to the 0, which is 8 times 1, which is 8. Cool. Question, Reed? Oh, yeah, thank you. I was actually, good reminder. When you have a chance, also, Caroline, fill out the attendance form, but it's as long as you do it before you leave. All right. So, and Caroline, did you have a chance to watch the video from class on Friday? Cool, good, because we definitely did a lot of first order linear examples there. We'll do a couple more today, but I was focusing more on solving differential equations with particular solutions, just because there's a few of those on your homework, and it's due today, right? It's due today. Yeah.
I feel like, and also in like the way he writes his questions in class, like really makes sense in my head, and then
Sure.
so
Right, and I was looking at the homework, like not that I've seen his lectures, but like I was looking at the homework, and it just the questions like that. Actually, that question that we just did is similar to one of the homework questions. Like I kind of modeled after that, and actually the rest of these are also kind of similar to the homework questions. So if the homework is a little troubling, these should be somewhat helpful for those as well. But that's also an excellent resource. So if I want to solve. So this is one of the ones we just looked at, one of the separable differential equations. If we have dy dt equal to 60 times y times t to the 9th, suppose that the y-intercept of the solution is 5. What is the particular solution y of t? So if I was writing this question or thinking about this question, I would take this piece of information right here and think about what that meant functionally. So if the y-intercept of the solution is 5, okay, well, my solution is y of t equal to something. If the y-intercept is 5, that means that y is equal to 5 when we plug in what? Right, when we plug in 0. So this here just means y of 0 is equal to 5. So now we're going to use that once we get to after we get our general solution, then we'll use this information to find the particular solution. Okay. So if we're solving dy dt equal to 60 times y times t to the 9th, we already observed before that was separable. I'm going to point out again, just because I think it's good to know, what's the function here? Is it y or is it t? Right. I mean, your gut would be y. Y is usually fine. Rarely will y be the independent variable, although it certainly could be. But just really, whenever I'm thinking about it, I'm just looking at my derivative and saying whatever variable is on top is my function. Whatever variable is on the bottom of my dy dt is the independent variable or the input. So rewriting this so I can solve it, I'm going to have 1 over y times dy equal to 60 times t to the 9th times dt. And then we're going to anti-differentiate both sides. The antiderivative of 1 over y dy is equal to the antiderivative of 60 times t to the 9th dt. Let's see, actually doing the work. So normally I would write natural log of the absolute value of y if I'm anti-differentiating this stuff, but really, as long as you are careful, you don't have to worry about the absolute value. I'm going to jump straight to saying the natural log of y is equal to the antiderivative of 60 t to the 9th is going to be 60 t to the 10th over 10 plus c. And of course, the 60 over 10 is going to reduce down to 6. So then we're going to say that y itself, if we do e to both sides, e to the natural log of y is going to equal e to the 6 t to the 10th plus c. And this is the step where you have to kind of make sure you do it the right way. So e to the natural log of y is, of course, just going to be y. So we're going to get y equal to, and here's where you have to break this apart into e to the 6 t to the 10th times e to the c. And then we're going to call it, what's he calling it in class when he does this? Is he calling it a? Okay, that's a very typical choice. It's my preferred choice. So we're going to write this as y equal to a times e to the 6 t to the 10th, where that a is your e to the c. Now, I'm kind of being a little loose here. Technically, a is plus or minus e to the c because of the absolute value that we dropped before. The thing, all you need to know is that when you go from here to here, if you're not thinking about the absolute value, you just have to remember that a can end up being positive or negative. It's totally fine for a to be negative. But like it's confusing to think of it being positive or negative if you're thinking of it as e to the c, because e to the c is always positive. But really, it's plus or minus e to the c. So if you get to the solution here where you've got a times whatever your function is, just remember a can be positive or negative. And it should have made it so it came out to be negative. Oh well, I didn't. I guess I could change it. We could say that the y-intercept of the solution is -5. Make it more interesting. And then we've got our general solution. And if we plug in 0 for t, we know that y of 0 should equal a times e to the 6 times 0 to the 10th. And that should equal -5. And you're going to get a lot of e to the zeros when you do this. I mean, not always, but often. This is e to the 0. That's just 1. So we end up getting a equal to -5. So then our particular solution is going to be y of t equal to -5 e to the 6 t to the 10th. Questions about that? Cool. Yeah. Let's do some more. Yeah, I think I have one more thing already written up here. Yes. Oh yeah, this one's not that exciting, but fine, it's still good work. So you're gonna see I don't know, you'll probably see this type of differential equation often because it comes up a lot, where the derivative is equal to a multiple of your function. This is your general, right? This is just your differential equation that leads to the exponential growth model. Because all this says is that the rate of change of y is 13 times y. So if you're thinking of y as like your population, you're saying the rate of change of your population is 13 times however big the population is. And as the population grows, it grows faster and faster. And so that's how we get exponential growth. We could totally solve this, right? Here is the solution, but solving it's easy. I mean, compared to other differential equations. Solving it is, again, a separable differential equation situation. dy divided by y equals 13 times dx. And then we anti-differentiate both sides. And we end up getting the natural log of, okay, I'm going to write the absolute value this time, just to remind, I know has your teacher talked much about the absolute value, or is he just kind of?
He stipulates in the question that x is greater than 0.
Oh, okay, well, there you go. Sure. If you didn't stipulate that, you'd have this. Natural log of absolute value of y equals 13x plus c. And then we would say, oh yeah, absolute value of y is equal to e to the 13x plus c, which gives us the absolute value of y is equal to e to the 13x times e to the c, which we would then say y equals plus or minus e to the c times e to the 13x. And there's your a. But again, you can totally kind of bypass that and just jump straight to the end where you're like, oh yeah, e to the c is just. Okay, so we didn't need to do any of that, right? So I should point out, I'm doing more work than I need to here, right? If you're doing this sort of homework question, you shouldn't do all this work because they've already given you the general solution. They're just really asking you to figure out what c is for the particular solution. So if I know that y equals a times e to the 13x, or you can call it c, it doesn't matter what you call it. And I know that y of 2 equals 9. Well, let's find a. All right, so if y of 2 equals 9, what am I plugging in for y? 9 or 2? 9. So 9 equals a times e to the 13 times what I'm plugging into for x. And this one's not going to be very nice, right? We're going to get 9 divided by e to the 26th power is equal to a. So then we can write our particular solution. I do have to stress, and I know I've stressed it a few times already, but I'm going to stress it again. You can't stop when you find the constant. You have to go back and then plug in the constant to the general solution to write your particular solution. The particular solution here is y, or if you prefer, y of x equal to my a, which is 9 over e to the 26th times e to the 13x. I will also say you might see someone rewrite this as y equal to 9 times e to the 13x minus 26. Because if you have e to the 13x divided by e to the 26, you're just subtracting those exponents, which is exactly 13x minus 26. Also, if you write it this way, you can see that when you plug in 2 for x, 13 times 2 is 26, 26 minus 26 is 0, and e to the 0 is 1, and 9 times 1 is 9, so you get 9. So it works. But sometimes people, especially when you get like a not very nice constant in front like that, people often kind of combine the e to the whatevers to do that. Okay, let's look back at some first order linear examples. Yeah, cool. Let's look at this one. Where'd you go? X to the 4th times y prime plus x cubed times y equal to x squared. I haven't done this problem, so I don't know if it's going to turn out nicely, if it's going to really suck. Sometimes they really suck. It's okay. So let's first, we recognize it's first order linear, but it's not written the way we want to write it. So we have to get y prime isolated. We have to isolate y prime. We divide everything by x to the 4th. You can show as little or as much work as you want here. I'm showing all the work. So I'm getting y prime plus 1 over x times y equal to 1 over x squared. It's not really important to identify your q of x. You just have to recognize that the right-hand side is just some function of x. It shouldn't have any y's in it. But it is important to recognize that your p of x is the thing that's multiplying y. So obviously when you're doing a homework problem, you can solve this however you want. Has he talked about how much work he wants to see if you have this kind of question on an exam? Like, does he want you to show all the steps?
Today in class,
Mhm.
like this little sheet of steps.
I'm sure.
Like,
Okay, yeah, that's okay. He probably wants you, at least for now, we should show all the steps. So the steps are always the same. They just, I mean, the same, I should say, in that we're doing the same sort of thing. They might differ from each other in that sometimes they're going to be harder, sometimes they're going to be easier. But the first step is to find your integrating. Well, I should say that was the first step, was to isolate y prime, to write it as y prime plus p of x times y equal to q of x. So that was our first step. And then our second step is to find the integrating factor, which he is calling it u. It's terrible. We'll call it mu, just because it looks close enough to u, but it's usually called, in most classes they do call it mu of x, and it's equal to e to the integral of p of x. And even if we don't stipulate that x is positive here, we don't bother with any absolute values. We need to get a natural log. So it's going to be e to the natural log of x, even though I tried to write the absolute value there because I can't help it. And then that's going to be just x. It is always in your interest. I don't want to say always. It is probably always in your interest to simplify this integrating factor as much as possible. So if you have e to the natural log of something, you should definitely make that nicer. All right, and then we multiply everything by it. Multiply our equation, our differential equation, by mu of x equal to x. Okay, this one's going to be kind of boring. That's all right. So we're going to get x times y prime plus x times 1 over x times y is just 1 times y equal to x times 1 over x squared is just 1 over x. Yeah. Oh, really? What does he do?
He does 1 over the integrating factor times the integral of q.
Oh, so he jumps to, so he's skipping. So cool. So here's the words. I'm kind of showing all the steps, and he's jumping straight to the end. which is totally fine. Caroline,
No, I was just
okay,
like, I was thinking like you did, and I was like.
sure. So let me show you, let me do these steps and then we'll talk about that in just a second. So what I want you all to see here is that this left-hand side is always the derivative of a product. And specifically, it's always the derivative of the product of whatever you have multiplied by y prime times just y. So what I really just do is I look at the thing that has y prime and I say, oh, x times y prime, I'm just going to rewrite that as x times y. Just drop the prime. And then think of that as a product rule where we're taking the derivative of that product. Let's take a look. If I take the derivative of this product, I do the derivative of y times x plus the derivative of x times y. Totally a product rule. Always a product rule. That's why we do this whole integrating factor thing, is because it makes it so that left-hand side always comes out to be a product rule. Now, you'll see in a second, you can always skip this step. Or you can skip straight to the end. Here's why. So I will also point out that this right-hand side over here, we multiplied our q of x by our mu of x to get this. So this really is q of x times mu of x. And this really here is the derivative of mu of x times y. Okay, so here's what we've got. We've got x times y, derivative of that equal to 1 over x. And then if we want to solve this, well, if the derivative of x times y is equal to 1 over x, then x times y is equal to the antiderivative of 1 over x. Cool? Okay. And then finally, well, maybe not finally, but I'm going to write it this way to do it. If we solve for y, we're going to get y equal to 1 over x times the integral of, I'm going to write this more suggestively as 1 over x squared times x. So what I want you to see is that this is exactly what he said it would be. This is 1 over our integrating factor times the integral of q of x times our integrating factor mu of x. So the good news is he's not expecting you to show all this work. We can jump straight from having found the integrating factor. So we can jump straight from step 2 all the way down to step 5. Even though my numbering is not particularly the same anytime. I'm always like, oh, here's another step. Here's another step. My numbers are probably not very standardized here. So we can always do this. Great. We'll do that for the next one. Here, finishing it off here, we're going to say, okay, y is equal to 1 over x times the integral of 1 over x, which is going to be 1 over x times. Now here I would put in the absolute value. So it's going to be 1 over x times the natural log of the absolute value of x plus c. Now it is really, really, really important to make sure that that 1 over your integrating factor multiplies by the entire thing, including the constant. I usually like to multiply it through because sometimes some stuff cancels. Here it wouldn't really, but I would still probably choose to write this as y, or y of x is equal to the natural log of the absolute value of x over x plus c over x. That's probably how I would choose to write my answer. You can write it as one fraction, I guess. I just find it less fun, I guess. So I don't have a good answer for that. Questions about this before we do another one? We'll do the next one the short way. Okay. But I should strongly emphasize this is why it works. Because every time you do this, you're multiplying by a thing so that the left-hand side becomes a product rule. And it always becomes the product rule of y times whatever your integrating factor was. And so then to solve for y, you integrate both sides to get y times your integrating factor, and then it's the integral of your integrating factor times q, and then you solve for y. If you look back at the notes from class on Friday of last week, there is definitely, this is written out in very kind of general terms. In fact, let's take a look real quick just to see it here. Yeah. So here it is written out in just terms of Y and P and Q. We have this, whoops, you can't see that. We want to have this format. We find the integrating factor, mu of X. You don't need to write this down. You can find it later. And if we multiply both sides by mu of X, you get Y prime times mu of X plus Y times P of X times mu of X equal to Q of X times mu of X. And it's really, really important to notice here that if you have mu of X equal to e to the stuff, the derivative of mu of X is the derivative of e to the stuff. And the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And the derivative of the antiderivative of P of X is P of X. So then you end up getting exactly a product rule here, right? This is Y prime times mu plus Y times mu prime, which is really just the product rule of Y times mu. So we get Y times mu derivative equal to Q times mu. And then if we solve for Y, we anti-differentiate both sides and then divide both sides by mu. So we get exactly the shortcut answer. But the nice thing about this is you can totally jump from, oh, I found mu of X. Great, we can jump all the way down here. So there's our answer. I mean, we're not done when you get here. You still have to multiply these two things together, do the antiderivative, multiply by 1 over mu, possibly solve for a constant. Yeah, like there's a word there I'm looking for. But yeah, so that's nice that he's saying you can do it this shorter way, because it definitely is a lot to write it out every time. Also, no one could ever check if you're doing web work, right? Like, did they write? I mean, there's probably ways you could ask the questions so that you could be like, what's the left-hand side of the derivative of as a product rule? You could ask that, I suppose, and have to make you think about it. Let's look at, sure, that's not a terrible problem. Let's look at that one though. No, not that one. That one, sorry. Sure, let's do this one. Let's do Y prime times cosine squared of X plus Y equal to 1. We're going to solve this. And then after we solve this, I'm going to make up an initial condition so we can solve for the particular solution. Also, for those of you who joined, please do fill out the attendance form when you have a moment. Oh, it's the same person. I just didn't see your name. In case you didn't fill it out before. Okay, so first things first. Is this separable? Like, I know we're thinking first order linear because it's written in a way that's kind of first order linear, but I would always at least kind of think about, can I do this separately? Like, you know what? I could do this separately. So that's a question you have to ask yourself. Even though you can do it separately, is it the better way? I don't know, honestly. Like, so let's talk about doing it first order linear. So I'll point out we could do it separable. We could say Y prime equals Y prime times cosine squared of X is equal to 1 minus Y. And then we could totally say dy dx times cosine squared of X equals 1 minus Y. And then bring over the 1 minus Y. So you have 1 over 1 minus Y dy equals 1 divided by cosine squared X dx. Or actually what I'd write is the integral of 1 over 1 minus Y is equal to the integral of secant squared of X dx. So this one is separable. Let's finish. We might as well finish it now, but we'll do it the other way too, just to see the other way. So let's see. Integral of 1 over 1 minus Y. It's kind of like this. I guess I won't write the absolute value, though it hurts my heart not to do so. What am I missing though? Yeah. And then that's going to equal the antiderivative of secant squared, which is good old tangent of X. Okay, we got to solve for Y, so put the negative over there. The natural log of 1 minus Y equals negative tangent of X. Still plus a constant, because a constant times -1 is still a constant. E both sides. Then you have 1 minus Y equal to e to the negative tangent of X plus C, which is going to end up being times e to the C, which is going to end up being A. Right? It's always the same thing. And then solving for Y, we're going to get I'm gonna bring this stuff to the left, so 1 minus a times e to the negative tangent of x is equal to y. How about that? Cool. It is neat that you can solve these either way, and the answer, as long as you do enough simplification, does come out the same. Let's do it the other way, though. Okay, so first things first, we need to write it as y prime plus p of x times y equal to q of x. Specifically here, we have to divide everything by cosine squared. So we're going to have y prime plus 1 over cosine squared x times y equal to 1 over cosine squared x. And we definitely need to recognize that our p of x is 1 over cosine squared, which is certainly going to be easier to think of as secant squared. Right, because we're trying to anti-differentiate p of x, and it's definitely worth our while to write it in a way that looks more recognizable. So our mu of x here is going to be e to the integral of secant squared of x, which is going to be e to the tangent of x. And then, even though it feels weird to me, we're just going to jump to the almost end. So our solution is going to be y equal to, I like to write it out the long way first, 1 over mu of x times the integral of q of x times mu of x. Well, that's going to equal 1 over e to the tangent of x times the integral of q of x, which is secant squared, right? That's my q of x right there. I do want to write a secant. I mean, probably I want to write it as secant squared. And then our mu of x was e to the tangent of x. Indeed. This is not terrible to integrate. I know it's not terrible because this answer over here ended up being pretty easy. So we could do it the long way. A long way is kind of a misnomer here. We should be able to see that this is a u substitution, right? If you let u equal tangent of x, your du is exactly secant squared x times dx. So we do u equal to tangent of x. Our du is secant squared x dx. And this just becomes the integral of e to the u. Du, which is equal to e to the u, which is equal to e to the tangent of x. So this whole thing right here, this is really just equal to 1 over e to the tangent of x times the antiderivative of this, which is e to the tangent of x. Now, if we forgot the plus c, it would be a really boring answer, because 1 over e to the tangent of x times e to the tangent of x is just 1. When you throw in the plus c, I'm going to say plus a. Plus a? Minus a. Fine. Sure. Plus c. Then we're going to get that our answer, y of x, is 1 over e to the tangent times e to the tangent is 1. And 1 over e to the tangent times c is c e to the negative tangent. And you can write plus or minus. It doesn't matter what you write there. You could have written a plus here because, right, it's a constant. You can change it. So these answers are the same. Kind of cool. Yeah, I guess that's okay. It's 10:49. I guess we can stop.